Usually when we watch a massive sporting event like the Olympics, we are cheering for the athlete who makes the most undeniable earth-shaking impact.
Oh, absolutely. The bigger the impact,
Yeah.
the better.
Right. Like
Yeah.
we want the runner who just tears through the finish line or the weightlifter who heaves the heaviest barbell and drops it with this, deafening crash. We want to see their power violently transfer into the world around them.
Yeah, we expect a huge display of physical force.
Exactly. But you watch the high diving event and the entire stadium is completely silent. Like everyone is holding their breath, hoping for the exact opposite.
It's so true. We're all applauding the athlete who makes almost no impact at all.
Yes. We want to see a diver who slips from the air into the water and leaves nothing but a tiny vanishing ripple. We literally applaud them for essentially deleting their energy transfer.
It really is a complete inversion of what we usually celebrate in sports. I mean, when an Olympic high diver enters the water without making a splash, we instinctively recognize that minimal disturbance as the ultimate display of technique.
Because it's just so incredibly hard to do.
Right. It shows perfect body control, incredible aerodynamics, and complete synchronization.
Huh.
But if we pull back and look at it strictly through the lens of physics, what we are really applauding is the fact that they managed to enter a dense fluid without creating a massive wave.
They avoided the splash.
Exactly. They avoided creating a chaotic disturbance. I mean, the energy of their fall didn't just vanish, obviously. They just managed to enter the water so efficiently that the energy slipped right through rather than exploding outward.
And that idea that energy doesn't disappear, but instead travels and disperses, is exactly where we are heading today. Welcome to the deep dive.
It's a great topic.
Today, we are immersing ourselves in the fascinating, invisible mechanics of the world around you. We're talking about waves.
The hidden architecture of basically everything.
Exactly. And to set our mission for today's deep dive, there's one absolute fundamental rule you need to keep in the front of your mind as we unpack these sources.
The golden rule.
Right. A wave is simply a disturbance, a back and forth motion that travels through something like water or air. But the crucial takeaway is a wave carries energy from one point to another without transferring matter. Energy moves, objects don't.
That is the golden rule of this entire framework. A wave is just a series of vibrations or oscillations traveling from one point to another.
It's energy in transit.
Exactly. Energy in transit. And once you start looking at your daily life through that specific definition, you quickly realize that waves are dictating almost every single thing you experience.
It isn't just about the ocean.
No, not at all. It's everywhere.
Okay, so here is our roadmap for you today. We are going to unpack the architecture of these invisible forces, the different dance styles they take as they move, how we actually measure them, and the specific environments they need to survive.
Sounds like a solid plan.
But let's start with that golden rule, because honestly, my instinct is to push back on it a little bit.
Oh, how so?
Well, the rule says a wave carries energy without transferring matter. But when I'm standing on the beach and a massive wave crashes into my shins, it absolutely feels like a whole lot of physical water just traveled across the ocean to hit me.
Yeah, it is an incredibly convincing optical illusion. And honestly, a very common misconception.
So what's actually happening there?
What you are experiencing at the shoreline is a breaking wave. The shallow ground disrupts the wave's structure, causing local seaside tides to physically crash. But to understand the pure mechanics of a wave, we have to step away from the chaotic surf.
Okay, where are we going instead?
Let's look at a deep, perfectly calm pond. Imagine you are standing on the edge, and you take a small pebble and drop it right into the dead center of the water.
Okay, I dropped the pebble.
The pebble hitting the surface is the initial disturbance. It transfers its kinetic energy, the energy of its motion, into the water.
Right, and you get those expanding concentric circles. The ripples just move outward toward the edge.
Precisely. Those expanding ripples are the wave carrying the pebble's energy outward toward the edge of the pond where you are standing.
But the water itself isn't moving to me.
Exactly. The actual water molecules in the center of the pond. They are not traveling all the way to the edge to wash over your shoes. The water is just the medium.
It's the vehicle.
Right. It is merely the physical substance that the energy is using as a temporary vehicle.
Okay, let's unpack this with another example from the sources, because I think it visualizes this perfectly. Imagine a boat sitting out in the middle of the deep ocean, far away from the shoreline.
A classic physics example.
Right. So when a wave passes under that boat on its way to the beach, the boat doesn't get pushed miles forward. The boat simply bobs up and down.
Yeah, it just rides over it.
The invisible energy carried by the wave is moving horizontally toward the shore, but the particles making up the wave and the boat floating on top of those particles actually just move in a vertical direction.
That bobbing motion proves the point entirely. There are two entirely different perpendicular motions happening at the exact same time.
So the energy and the water are doing two different things.
Right. The propagation of the wave is moving forward, while the particles of the medium are just moving up and down in place. They rise to let the energy pass, and then they fall back down.
So if we freeze that boat mid-bob, my instinct is that we can actually map out the structural anatomy of a wave.
We absolutely can.
If the calm, flat ocean before the wave arrives is our baseline, what is the official terminology here?
We call that flat, resting baseline the equilibrium, or the mean position. It is the state of the medium before the energy hits it.
Okay, equilibrium.
Then the disturbance arrives, the boat gets lifted up into the air, the absolute highest point the medium rises to its maximum displacement above the equilibrium is called the crest.
The crest, like the crest of a hill. And when the boat comes back down, dipping past that flat equilibrium line into the lowest possible dip before it starts rising again, that lowest point is called the trough, correct?
Yes, exactly. That minimum displacement is the trough.
Crest is top, trough is bottom.
Right. So any given particle in that medium is going through a continuous cycle, resting at equilibrium, pushed up to the crest, falling down through equilibrium to the trough, and eventually settling back.
And if I'm measuring this, my instinct is to measure the distance from that flat equilibrium line straight up to the top of the crest. That measurement is the amplitude, right?
Correct. Amplitude is the maximum displacement from the position of rest.
Got it.
But we shouldn't just view amplitude as a geometric measurement on a piece of paper. The amplitude is the direct physical indicator of how much energy the wave is actually carrying.
Interesting. So bigger amplitude, bigger energy.
Exactly. A massive, towering ocean wave has a huge amplitude because a catastrophic amount of energy was transferred into that disturbance, usually by severe storm winds.
And the pebble in the pond?
A tiny ripple from a pebble has a very small amplitude because the energy input was minimal.
Let's talk about the day in the life of one of those ocean waves, just to really cement this. It starts with a storm miles out at sea, right?
Yes. The wind transfers energy into the water, creating a disturbance.
And then that wave, that invisible packet of energy, travels across the entire ocean for days.
Sometimes thousands of miles, yes.
Just rolling under boats, making them bob up and down, but never actually dragging any water with it until it finally hits the shallows of our local seaside tides and crashes.
That's a perfect summary of its life cycle. Pure energy transit until the very end.
Okay, so the boat bobbing up and down, crests and troughs, that all makes perfect sense for water. But does every single wave in the universe force its medium into this vertical up and down motion?
Not at all. That brings us to a fundamental distinction in how energy navigates different environments.
The two different dance styles.
Exactly. Not all waves move the medium in that vertical pattern. That specific style of movement where the boat bobs vertically while the energy moves horizontally is called a transverse wave.
Because the motion of the medium is transverse, or perpendicular, to the direction the energy is traveling.
Exactly. Water waves are transverse. The seismic S waves that rip through the Earth's crust during an earthquake are transverse.
Or like a heavy jump rope. If you tie one end to a doorknob and whip your hand violently up and down, that S shape traveling down the rope to the door is a transverse wave.
Yes, another perfect example. But there is an entirely different mechanism for energy transfer, and it is called a longitudinal wave.
Okay, so if transverse is moving perpendicular to the energy, longitudinal must mean the medium is moving parallel to the energy.
Precisely. In a longitudinal wave, the particles of the medium don't move up and down at all.
What do they do?
They vibrate back and forth in the exact same direction that the overall wave is traveling.
So my brain immediately goes to that classic science class toy, the Slinky.
Oh yeah, the Slinky is the absolute best visualizer for this.
Right. If you stretch a Slinky out across the floor and shake one end up and down, you get that S shape. That's transverse.
Exactly.
But if you push and pull the Slinky straight forward and back,
The rings just kind of bunch up and then spread apart moving forward.
right, you can literally watch that tightly bunched section of coils travel from your hand to the other end.
Yes. In physics, we have specific terminology for that bunching effect.
Tip me.
In a longitudinal waves, those tight areas where the particles are shoved closely together are called compressions.
Compressions. Makes sense.
And the open stretches where the particles spread far apart are called rarefactions.
Compressions and rarefactions. So instead of a transverse crest and trough, we have a longitudinal bunching and spreading.
You've got it.
But do we actually experience this kind of wave in our daily lives?
You are utilizing one right this very second to listen to this deep dive. Sound is a longitudinal wave.
Wait, really? Sound is just bunching and spreading.
Yes. Sound is produced when an object vibrates rapidly.
Hmm.
When you speak, your vocal cords are vibrating.
Yes.
As they push outward, they violently shove the air molecules in your throat together, creating a compression. Those bunched up molecules bump into their neighbors, transferring the energy forward, and then bounce back, creating a rarefaction behind them.
So it's a domino effect. I'm not physically blowing a continuous stream of air from my mouth into the microphone or from the speaker into the listener's ear.
No, not at all.
The air molecules right next to my vocal cords just shove their neighbors, who shove their neighbors all the way across the room until the final air molecules violently shove against the listener's eardrum.
That is exactly how it works.
Which is why dolphin echolocation works so well underwater, right? I read that in the sources.
Yes, perfect connection. Dolphins use sound waves, those longitudinal compressions, to navigate.
And water molecules are packed tighter than air molecules.
Exactly. Because it relies on particles shoving neighboring particles, the density of the medium matters. Sound travels much faster through water than through air simply because the molecules are closer together, the dominoes are closer, so the energy transfers faster.
Okay, so here is where my understanding hits a bit of a wall.
All right, what's the wall?
If sound is just a traffic jam of air molecules and ocean waves are a traffic jam of water molecules, what happens when there are no molecules at all?
Ah, I see where you're going.
We've been talking entirely about mechanical waves so far, right? Waves that absolutely require a physical substance, a medium to travel through.
Yes, mechanical waves are strictly bound to physical matter. Whether it is gas, liquid, or solid, they need atoms and molecules.
Right.
If there is no medium, the chain reaction cannot happen. If you put a ringing alarm clock inside a heavy glass jar and pump all the air out to create a vacuum,
You won't hear anything.
exactly, you'll see the hammer striking the bell, but you will hear absolutely nothing. There are no air molecules left inside to compress. The energy has no vehicle.
Right. And that makes logical sense based on everything we've discussed. But space is a vacuum.
It is.
The distance between the sun and the earth is 93 million miles of absolute freezing nothingness. There is no air, no water, no physical medium.
None at all.
Yet when I step outside, I can see the sunlight and feel the heat on my skin. Light and heat are waves. So if they don't have a medium to travel through, how is that energy reaching us? What is waving?
This is one of the most profound paradigm shifts in physics, and it introduces us to the ultimate rule breakers of the universe, electromagnetic waves.
Electromagnetic waves.
Yes, they are fundamentally different from mechanical waves. They do not require a physical substance to travel through. They are perfectly capable of carrying immense amounts of energy through the total emptiness of a vacuum.
I have to push back here, though. You can't just give me the vocabulary term and leave it at that.
Fair enough.
We established that waves are disturbances. If there is no physical matter in space to disturb, how does an electromagnetic wave propel itself? What is the mechanism happening in that 93 million miles of empty space?
To understand the mechanism, you have to look at the name itself, electromagnetic. These waves are created by the synchronized oscillation of two invisible fields, an electric field and a magnetic field. When a charged particle vibrates, it creates a changing electric field. According to the laws of electromagnetism, a changing electric field automatically generates a changing magnetic field.
Oh, I see where this is going. It's a feedback loop.
Exactly.
Yeah.
It is a cosmic leapfrog effect. The collapsing electric field generates a magnetic field. As that magnetic field collapses, it generates a new electric field, which generates a new magnetic field over and over again.
So they just continuously create each other.
Right. They perfectly pull each other into existence perpendicular to one another, leapfrogging forward at the speed of light. They don't need a physical medium like air or water to carry them because they essentially are their own medium.
That is absolutely wild. They are just pulling themselves up by their own bootstraps across the entire universe.
It's a beautiful way to think about it.
And it's not just light, right? The sources mentioned engineers use these wave principles to build modern communication technology.
Oh, absolutely. Cell phones, satellites, Wi-Fi, they all rely on electromagnetic waves to send information through the air and through the vacuum of space without needing a wire or a physical medium.
Even our kitchen microwaves use them, right?
Yes, microwaves are just a specific type of electromagnetic wave. They pass through the air and directly transfer their energy into the water molecules inside your food, causing them to vibrate and heat up.
Okay, so if we summarize our big classifications here, you can have a mechanical wave, which needs a medium, like an ocean wave needing water or sound needing air.
Right.
And you can have an electromagnetic wave, like light or Wi-Fi, leapfrogging its own magnetic and electric fields through the pure vacuum of space.
A perfect summary. Different mechanisms, different environments, but they all obey the golden rule. They're moving energy from point A to point B without permanently transferring matter.
Okay, so to truly master this topic, we need to move beyond just the shape and environment of the wave. Let's talk about timing and speed.
The math side of things.
Right. We know amplitude measures the energy vertically. But how do we measure these invisible forces horizontally as they fly through space and time?
We rely on three fundamental measurements to understand the timing of a wavelength, period, and frequency.
Let's start with wavelength.
Wavelength is exactly what the name implies, the physical length of one complete wave cycle. Officially, it is defined as the shortest distance between 2 points where the wave pattern perfectly repeats itself.
So if I'm looking at our transverse wave drawing, instead of measuring from the flat equilibrium line up to the crest, which we established as amplitude, I would measure from the top of one crest straight across the gap to the top of the very next consecutive crest.
Exactly right, from crest to crest or from trough to trough.
And for the Slinky.
For a longitudinal sound wave, you would measure from the center of one tightly packed compression to the center of the next compression. It is the physical linear distance of one full oscillation, and it is usually measured in meters.
That makes sense. Distance is wavelength. But what about frequency and period? Because frankly, those two concepts always seem to get tangled up in the explanations.
They get tangled up because they are essentially two sides of the same mathematical coin. They are inversely related to one another.
Okay, break that down for me.
Let's look at the period first. Imagine you are standing on a pier, looking straight down at one fixed wooden piling in the water.
Okay, looking at the piling.
The period is the exact amount of time it takes for one complete wavelength to pass that specific piling. It is measured in seconds.
Okay, so period is asking, how many seconds does it take for a single wave cycle to go by?
Correct. Frequency flips that perspective entirely around. Instead of asking how much time one wave takes, frequency asks how many complete wave cycles can pass this point in one single second.
So it's a rate.
Yes, it is measuring the rate of occurrence.
And frequency isn't measured in seconds, right?
Yeah.
It has its own unit.
Right. Frequency is measured in a unit called hertz. If two complete ocean waves crash against the pier every single second, that wave sequence has a frequency of 2 hertz.
Let's connect this to something tangible. Rather than just reciting textbook math, think about it in terms of music.
Oh, that's a great application.
If I'm listening to a song with a very fast, high-tempo beat that relates to a high frequency, right? A huge number of beats are passing by me every single second.
Yes. High frequency mathematically requires a short period. The waves are packed tightly together.
Right. And conversely, a slow, low-tempo song is like a low-frequency wave. Fewer beats are passing by per second, which means a much longer period for each individual beat.
Exactly. And you brought up music, which relates perfectly to energy delivery, the most crucial part of this relationship.
How so?
Well, a fast, high-tempo song feels more energetic, right? In wave physics, particularly with electromagnetic waves, frequency is the ultimate dictator of energy.
Because if more waves are hitting you per second, more energy is being transferred to you per second.
Exactly. This is why different parts of the electromagnetic spectrum interact with our bodies in drastically different ways. Radio waves, which surround us constantly, have a very low frequency and an incredibly long wavelength.
They don't hurt us.
Right. Their low frequency means they carry very low energy, so they pass harmlessly through our bodies.
But if we jump to the other end of the spectrum,
At the other extreme, you have X-rays. These waves have microscopic wavelengths and extremely high frequencies. Billions of wave cycles are hitting a target every second.
which means high energy.
Massive amounts of energy. Energy so intense that it can actually pass through human tissue to show us our bones. The mechanism of the wave is exactly the same as a radio wave. It's just leapfrogging electric and magnetic fields. But the frequency entirely changes how that energy impacts the physical world.
It is genuinely mind-blowing when you step back and connect all of these dots.
It really is.
Okay, before we wrap up, let's do a quick quiz for you listening. I am going to throw out a concept from today's deep dive, and you see if you can remember the answer before our expert says it.
Ooh, the pressure is on. Let's do it.
Question 1. What do we call the absolute lowest point a wave sinks to?
That would be the trough.
Spot on. Question 2. Which specific type of wave can travel through the absolute vacuum of space?
The rule breakers, electromagnetic waves.
Perfect. And the final question. If you drop a pebble in a calm pond, are you physically moving water across the pond or just energy?
Just the energy. The water is just the medium, it stays put.
Awesome. And for any students listening, you don't need a lab to see this stuff. You can observe these concepts in your own backyard. Just fill a baking dish with water and tap the surface to watch transverse waves, or grab a Slinky to see longitudinal compressions.
Physics is everywhere.
It really is, whether it's a boat bobbing on a transverse water wave, a dolphin vibrating sound longitudinally through the ocean, or the electromagnetic light of your Wi-Fi router beaming through the air. It's all just energy on the move.
It fundamentally rewrites how you perceive your surroundings. We spend so much of our lives focused on physical matter, the water, the air, the solid objects around us. But matter is often just a canvas. It's just the medium.
I love that.
Actually, I want to leave you with a final thought to mull over, something that pushes the boundaries of everything we've discussed today.
I am ready for it.
We just talked about how electromagnetic waves can travel through the absolute emptiness of a vacuum because they generate their own fields. For a long time, we view the vacuum of space simply as an empty stage where these fields leapfrogged.
Right, an empty room.
But modern astrophysics has proven that the empty stage itself can wave. When unimaginably massive events occur in the universe, like two black holes spiraling into one another and colliding, they display so much energy that they literally create gravitational waves.
Wait, meaning the vacuum of space itself is the medium?
Exactly. Gravitational waves are ripples in the actual fabric of space-time. They stretch and squeeze the very dimensions of reality as they travel outward at the speed of light. It proves that even absolute nothingness is a medium that can carry a disturbance.
So there really is no escaping it. You aren't just passively sitting in a room right now. You are sitting in the middle of a continuous, overlapping, microscopic relay race of vibrations that stretch from your vocal cords to the edges of the universe.
It's quite the perspective shift.
It really is. Thank you for joining us on this deep dive. Keep looking for those invisible ripples, and we will catch you next time.